Alright guys, so let's start off with this example first. What I want to do today is give you one example of an area that you should integrate in terms of y and one that you should integrate in terms of x, while also giving you some practice with some of the other stuff that's challenging, like trig functions and figuring out how the graph is enclosed. So in this case we have a parabola of some kind and a straight line. So the parabola, because it's in terms of y squared, we know that it's going to be sideways facing. We could solve this in terms of y and get 12 minus y squared over 4 equals x, or x equals 3 minus y squared over 4. So we have an idea based on that what the parabola looks like. We know that it's going to start at x equals 3, and because of the negative sign in front of the y squared, we know that it's going to be facing towards the left. So it's going to open up like this. And then our other function is pretty easy. It's just a diagonal line, x equals y. So it looks like we have two intersection points that are going to help us define the region enclosed. And again, if we were to try to integrate this in terms of x, then we would be making vertical boxes, and we'd have a problem right in this region where we switch from the line being the top function and the parabola being the bottom function. And then in this region, we switch to the top of the parabola being the top function and the bottom of the parabola being the bottom. So it's going to require more than one integral. So it's not ideal. So what we can do instead is integrate in terms of y. And if we integrate in terms of y, then our boxes are going to be arranged like this. And you can see that this is more well behaved. The parabola stays as our top function the entire time, and the line stays as the bottom function the entire time. It also is beneficial because the parabola is in terms of y, so we only need one function. We don't need this square root function plus or minus. So the top function here is going to be 3 minus y squared over 4, x equals. And the bottom function here is going to be x equals y. Okay, so now we need to find the points of intersection. And we can set the two functions equal to each other and solve for the points where y is equal. So we're going to go ahead and do that. So we're going to say our two functions are x equals 3 minus y squared over 4 and x equals y. So we're going to replace the y, or sorry, replace the x. So we'll have y equals 3 minus y squared over 4. We might want to put this back into the form that it was before, just so we don't have random fractions sitting around. So we'll have 4y equals 12 minus y squared. So we'll have y squared plus 4y minus 12 equals 0. And then we can factor that to get the points for y. So in this case, we're going to have y equals negative 6 or um, 2. Okay. Um, so if we go back up to our graph, because this is a line where x equals y, we know this point is negative 6, negative 6, and we know this point is 2, 2. So what we're going to be doing is we're going to integrate in terms of the functions. We're going to be integrating in terms of y, so that means we're going to be sliding from negative 6 up to positive 2 for our integral. And we're going to be making those boxes in the horizontal direction. So each of the boxes is going to be built horizontally, and they're going to be stacked vertically up like that. That's how we should think about this this integral that we're about to make. So the integral should go from negative 6 to 2. The top function was 3 minus y squared over 4. And the bottom function was x equals y, so we'll have minus y. And that whole thing's in terms of y. So when we integrate that, we'll get 3y minus y to the third over 12 minus y squared over 2. And we need to evaluate that from negative 6 to 2. And that's going to give us, when we evaluate with at 2, we're going to get, let's see, the 3y, we're going to get 6, and the negative y cubed over 12, we're going to get negative 2/3, and then we'll get negative 2, minus, and then we need to evaluate at negative 6, and it looks like we're going to get, let's see, for 3y, we're going to get negative 18, and for y cubed over 12, we're going to get negative 18 and 18. So that comes out to 64 over 3. Okay, so there's an example of a problem that integrating with respect to y was a lot easier. And we also needed to determine the interception so we could define the area enclosed by the two regions, or the two curves.